going to talk about the trends of the periodic table. What I need you to do is in your top right corner of the, left corner of your foldable, you want to open up where it says trends of the periodic table and write down this information so that you know what parts of the periodic table are involved and the different definitions that we need to know. You can pause me now while you copy everything down. Alright, so some things that you might not recognize is shielding, and then nuclear charge is just your increase of protons in the nucleus. As you go across, we're adding protons, and that adds to your nuclear charge. And that will explain a lot of the reasons behind the trend. So let me explain what shielding is. Shielding, if you think about the old Bohr model where you have your, grab a pen. Why the pen's not working. Well, maybe it would help if I change colors. Let's go with that. Okay, shielding is when you have your nucleus, and then you have that first ring, and then you have the next ring, and then the next one, etc., etc., etc. We have 7 rings, right, guys? The electrons that are on this third ring are shielded from the nucleus by the electrons on the first and second ring. We'll actually talk about them not being rings in the next lecture, but that kind of gives you an idea of what shielding is. And it's constant across the period because you're adding to that same ring or whatever you're working with. But obviously it'll increase as you go down, because every time you go down a group, you're adding another ring to that group. Okay. So take a moment to pause me and copy down the notes behind the atomic and ionic radii. Alright, so the reason the atomic radius decreases going across the period is because as you go across the period, if you're going from lithium to beryllium all the way to fluorine, you're within the same row, but you can visually see right here that the atomic radii are getting smaller. And that's because as you go from lithium to beryllium, to boron, etc., you are adding protons. And as you add protons, you're also adding electrons. And we know from magnets that positives and negatives attract to each other, so as we're going across, it ends up adding where it's a smaller, tighter pull because those positives and negatives are working with each other, coming closer and closer together. When we are looking at increasing top to bottom, well, if you think about the same thing, it's dealing with your shielding. Every time you go down a groove, you're adding another energy level, and so therefore you're going to get larger there. And yes, I know my drawing is ridiculous. I don't know how to draw circles. Your ionic radius, that is where you, nope, that's not what I wanted it to do. We'll look at sodium. So you see from sodium, whoops, sorry. Let's go with potassium. I haven't covered that one up yet. Potassium element is much larger than its ion. Well, as you're going, when it becomes an ion, and we'll talk more about ions and the charges and everything else in the next unit, but it's losing an electron, remembering that it wants to have a noble gas configuration of argon. So what happens when it loses that one electron out there, you're dropping off an entire energy level. So if we look up here, this whole energy level will go away, and so you are dealing with just 2 energy levels instead of 3, or in this case 4 instead of, or 3 instead of 4, since we're talking about potassium. Well, on your nonmetals, look what happens with your nonmetals. You have fluorine right here, and it's adding an electron to have its 8 electrons, but it still only has the 7 protons in there for that valence electron. I know there's 9 protons total, so we're ending up with 10 electrons, so you no longer have that 1-to-1 ratio, so the electrons have to kind of open up to allow that extra electron in there. All right, ionization energy. You're moving to the top right corner, so pause me and write down the notes real quick. Okay, as we're going down a group, you can visually see that the energy is getting lighter and lighter and lighter. Well, if you think about it, if here's your nucleus, and you're going down a group, that outer electron, it's very difficult because of all that shielding to hang on to an electron that's way out there. Whereas if the electron that's right next to the nucleus is going to be harder to take because it's really close to that proton. As you're going across the period, you can see from lithium to beryllium, the general trend here is to increase. Because what do we know about fluorine? We know that fluorine has 7 valence electrons, and it's very small. You can look back at your atomic radius picture. It's very small. So those electrons, because they had that positive-negative pull, is hanging on tight. And if you also remember that electrons want to have, or elements want to have 8 valence electrons, fluorine only has 7, so it wants to gain 1, not lose any, so it's not going to let go of anything. Now these anomalies where it kind of goes up and then down, and it's going up and then down right here, I will explain in the next lecture, because that deals with the electron configuration in the orbitals. Okay, moving to the last part. Pause me, copy the notes, unpause me, and let's go. Alright, you will never have to memorize these numbers. They will always be given to you. Fluorine is the most electronegative. It's the opposite of ionization energy. Your ionization energy is energy to make it an ion, removing the electron to make it an ion, whereas electronegativity is that ability to attract electrons. We're going, sticking with the thought of fluorine's very small radius. It only wants 1 more electron, and it's adding that electron to where it's really not that shielded from everything else. So fluorine is the most electronegative. It has the greatest ability to attract an electron to it. When you look at your halogens, you can see that it's going down because as you're going out from the nucleus, it's having a hard time keeping up with that 1 electron out there for cesium. Well, that 1 electron out, it's easier to get rid of that electron than trying to attract something else in order to fill its orbital, which we'll talk about orbitals later. It can happen, it just does not happen very easily or readily. If it didn't happen at all, it would have a 0 number here, but it obviously does happen. It's just very difficult with all the shielding that's there to attract an electron. So here's a summary of all the trends going across the period and going down the period. Again, we only deal with, you probably have these numbered as 13, 14, 15, 16, 17, 18. We only deal with the first 2 columns and the last 6 columns when we are talking about our trends. If you have any questions on trends, let me know. See you in class.